Yeah, welcome to the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse, and I'm here with...
Robert Moore. Nice to see everybody again.
We're broadcasting live from the campus of the University of North Dakota here in Grand Forks, North Dakota. Don't forget we have a live chat, so you have any questions for us, please do not hesitate to send us some questions. Also, just up front, we'd like to say that, of course, the opinions expressed by Robert and I are our opinions only and not necessarily opinions of the University of North Dakota, nor the College of Arts and Sciences, nor the Department of Physics and Astrophysics. So, Robert, today we're going to kind of dive into a little bit regarding the title of this podcast, that is the Cosmic Pie.
Cosmic Pie.
Now, if you want to bring up the first slide.
All right. Let me get my cursor over here where I can find it. There it is. So the first slide, there we go.
Okay, so in the first slide, what we see here is the Cosmic Pie. This is the origin of the name for the podcast itself. And what it is really a breakdown or the composition of the universe as a whole in terms of what is the dominant, different forms of matter, if you like, what dominant or not, and what is the different forms of energy that our universe contains. Now, as we see from this pie, this is a pie which is always divided into three pieces. The major part of the pie, that is the majority or the largest slice, is one which is labeled dark energy. It represents approximately 70% of the universe. So what is dark energy? So dark energy was discovered observationally back in 1998 by two independent teams of astronomers. And what they discovered was that the expansion of the universe is actually speeding up or accelerating, not slowing down. Now, the slowing down was expected. In fact, back in the 1920s, so almost 100 years ago, we discovered that the universe was in a state of expansion. And if you watch how that expansion should change with time, one of the things you would expect is, well, given the fact that the universe contains matter and energy, we know, therefore, there is gravity. And a gravitational force always comes in one flavor, as I like to say, unlike ice cream, right? It's always an attractive force.
Well, unlike electromagnetism or the other forces, we'll just leave it at that.
Right. So because gravity is an attractive force, one would think over time that rate of the expansion of the universe should slow down. You know, a good analogy for that, of course, is if you throw a rock up in the air. So what happens to a rock, Robert, when you throw it up in the air?
I don't know why. It keeps on going. No, it slows down and eventually stops and then starts to fall.
Right, and that's gravity, of course. It's in the gravitational field of the Earth. So the rock will have its maximum speed in the upwards direction as soon as it leaves your hand if you're throwing a rock up. Mm-hmm. From that point on until it reaches its highest point, it's always slowing down, slowing down, slowing down.
Well, I'm going to bring up the matter that even if you throw it fast enough that it can escape Earth's gravity, in other words, escape velocity, it's still going to slow down as it leaves Earth's gravitational field. So, yes, you would expect the universal expansion to slow down.
Right, and that's because the force that counts at that point, neglecting air friction, is the gravitational force that's pulling it back towards the Earth, slowing it down. So when we think about the universe as a whole, then it's the combined gravitational force of all the matter and energy that's in the universe that should cause the rate of expansion to slow down. So the expansion rate gets slower with time. So in 1998, what was thought initially, and when you do science, of course, it's not like you say, oh, I'm going to measure this thing, and somebody would say, well, what's your motivation for measuring? I don't know. I just want to measure it, just for some sake of getting information. Most scientists, when we approach different things, whether it's observations or experiment, you have some idea of what you tend to find, right? It's not like it's blind completely, right? You're just like, well, I think, I'm going to measure the slowing down of the universe.
It's the very rare thing, folks, that just jumps out and surprises you. You usually have some expectation of, oh, this is what's going to happen. Wait, what?
Yeah, so in that sense, serendipity sometimes will lead you even to the Nobel Prize, right? And we've seen that happen in the past. But in this case, the expectations were that the universe is slowing down. In fact, astronomers labeled that slowing down, and it was known as the deceleration parameter. So it was a goal to go measure that deceleration parameter to find out how much the universe is slowing down by. And that actually corresponds directly to the total amount of energy and mass that we have in our universe. And from that, you can tell certain interesting things like what is the curvature of the universe, if it has any.
If it has any.
You could have zero curvature and be flat, or it could have positive curvature, And that's like the surface of a sphere, like a basketball,
Right.
that way. Or it could have negative curvature, which is like the saddle of, or a surface of a saddle, or if you like, the surface of a Pringle chip, right? To use a more modern.
I like Pringles, so yeah.
And so to try to figure out which of those universes we live in, you can go out and measure the deceleration parameter, and that would help you to determine, which one it is. Hopefully, I mean, if we get, there are situations where we could get where the universe's curvature is just so mild, a little bit positive, a little bit negative, the uncertainties mean you can't really tell exactly what it is. It's just close to being, no curvature at all.
Right.
So there's always uncertainties in all of our measurements in science, of course. That's the way science works. Now, the interesting thing about 1998 is when astronomers went out and measured the deceleration parameter, what they discovered was the universe is not slowing down its expansion rate. It's actually speeding up. So we say that the universe's expansion rate is accelerating. Cosmic acceleration, which was later named dark energy. Now, what causes the speeding up of the universe?
If I can get in there before you do go into that, the reason we call it energy is because what causes an acceleration is essentially the system is gaining more energy. So, a force is acting on it to produce that.
So in other words, we know there's something else in addition to gravity.
Right.
That's at play. At the universe as a whole.
Mm-hmm.
Right? It's not one of these localized things where it's some frictional force acting on an object that's moving along the surface of a table, for example. We're talking about something that involves the universe completely. Right?
The whole thing.
The whole thing. So what is this dark energy? Well, we're not quite sure where it comes from. There was an interesting result that was published this week. I don't know, Robert, if you've seen this. And it was the tie-in between black holes and dark energy.
I've seen that. I didn't read the articles, but I've seen them talking about that, yes.
Yeah, so the premise in that study was that black holes accumulate mass over time through different mechanisms. One way is accreting of material, right? You can have gas or particles or other stars that just happens to get too close to a black hole and it falls in. It can't escape. So that ultimately, of course, would add to the mass of the black hole itself and increase its mass as more material falls into the black hole. The other way, of course, is you can have merging black holes. So two black holes, let's say, are in orbit around each other, so-called binary black holes. And because that system will release energy, and it's in the form of gravitational waves, which we talked about in a previous podcast a little bit. If you didn't catch that, of course, you could think of gravitational waves as sort of undulations in the space-time around us. And so the important point in this issue is that energy gets released from the system. And as energy gets released from the system because of the emission of these gravitational waves, these black holes will spiral towards each other, get closer and closer and closer until finally they merge. And so, some amount of the total masses of each of those black holes will result in the total mass of the one black hole that forms from the result of the merger. Now, some of that mass gets dumped into gravitational waves. So not all of it ends up in the mass of the final solitary black hole. That's the result of the merging process. So the thing was, you have these two ways that a black hole can accumulate mass. Through the gas and stars and dust falling into the black hole from an accretion disk or otherwise, and then the merging of black holes. And by the way, the merging of black holes was something that was discovered way back in 2015 when we first detected gravity, around that time. I can't remember the exact year now. But when we first detected gravitational waves.
That was the first gravitational waves that were detected, weren't they?
Right, and so there's been tens and tens and tens of candidates of these merging black holes as well as other objects like there's a condition where we have a neutron star merging with a black hole or even two neutron stars that merge together. But the vast majority of these gravitational wave detections so far have been with these merging black holes.
Right.
So we have proven observationally that this happens. So black holes, therefore, can accumulate mass over time because of these different processes. And what this latest study suggested was that black holes actually are accumulating more matter than can be explained through matter coming in via accretion of material or through the merging process. And they suggest that this additional matter is a result of energy in this case dark energy, being absorbed by the black holes themselves. Okay. Now I know it gets a little technical here. There's a lot of fine detail one has to worry about it. So it's a thought, it's a suggestion. They claim the observations are consistent with that idea, but of course it requires further study, as we always say.
I want to see another study finding the same thing before I'll start going, yeah, okay, that sounds about right then.
If you don't look at the study in detail, one of the things you might think about is, how do you know the exact amount of material
that falls in?
That falls in, either through the accretion process or otherwise. And that's kind of the thing you will always worry about. Now, if you looked at a large enough sample, you can do it from the point of view as a statistical type of argument.
Right.
But we have to be very careful, right? We want more than that. I mean, science is one of these enterprises or professions, if you like, where we always start off on the negative side of things.
Right. Don't believe it.
We don't believe anything, right? I mean, you have to show us the money, if you like, right? Show us the proof. Show us, and even when we see proof of something happening, we're like, well, I can think of a few other ways this could happen. So let's look at another study and another study and another study.
I will point out that this is where, a lot of studies in physics and astronomy, you'll see these term of some number, 6, say, and sigma. And it's because they're talking about this is how the 6 sigma is saying that there's only a certain amount of probability that this is random phenomena. And so, usually when you got 2 sigma, you're 99.6% sure, I think it is. So going out to 6 sigma is so close to 100 that you know something's going on. Let's find out what.
So the thing in science is what we need is the C word, confirmation.
Confirmation.
And that's how science works. You always start on the negative side of things. And until you're shown that this is the case, you always wondered if there's an alternative explanation, or maybe the observations or an experiment are just plain wrong. There's some problems, right? And we've seen that many times in the past. It wasn't that long ago, a few years ago, there was an experiment that was done in Italy. You may recall this, Robert, where they had suggested that there was evidence that neutrinos traveling faster than the speed of light.
Oh, I remember that one.
So they published a paper on this, and they basically said to the physics community, okay, this would be a fantastic experiment if the result is right. The result that comes out of this violates, Einstein's special theory of relativity and so on. But there may be a problem, right? We don't want to go there yet. So we like other people to look at this experiment to try to see if they can figure out where the issue is.
And they did.
And they did, and it turned out to be an instrumentation type of issue. And once that was corrected, then the evidence for faster than light travel went away. Okay, so you always have to be very careful. You can't just rely on a single experiment.
That brings up the point that sometimes you do go ahead and publish and put the information out there because, something's wrong, but your eyes aren't finding it. So please find where we're wrong.
And that's the whole publication process, right? People wonder, why do you have to publish your data? Why does it got to go through the peer review process, for example, right? Because you need to check this stuff, and people are human, so they make mistakes. Scientists can make a mistake, or you don't think of it quite the right way. We have unconscious bias, so we look for things that we think should be there and kind of ignore facts that go against it. There's all kinds of things you can think of why the peer review process is extremely important in science.
Yep.
And I always think of science as kind of like this random walk, right? So somebody is staggering around trying to get from one location to another. Eventually they get there, but they never go there on the direct route.
Right.
And that's kind of like science is like, right? We're staggering around. Sometimes we go down the wrong alley as we try to head home, and then we realize we're going in the wrong direction, and then we correct ourselves, and then we start heading towards the right direction. And eventually we get there. It may take a while, but...
And sometimes it's also just a matter of we got to the right place. We're just trying to go in through the window instead of the front door. And it's always a self-correcting process.
Yeah, that's an important thing, a self-correcting process, because even if several people, suggest something and then you come up with some other experiment that shows otherwise and turns out your experiment was correct and those others had that unconscious bias to say, okay, well, somebody else who had done this experiment prior to me I got the result that I think I'm getting now with my results, and then that can say, okay, well, mine must be right, and that may not necessarily be correct. We always need to check, double check, triple check, and so on. Any result, any experiment, any observations that's done in science.
And you're always looking for that thing is wrong. I can't emphasize that enough, and I'm talking with people. It's like you don't make a career in science by proving what everybody else has proved. You make a career in science by showing somebody else was wrong. So this idea that, we all just get together and decide, well, this is what we're going to say, it's like, yeah, that doesn't happen. You don't get very far showing what everybody else has shown.
Right, and that's why you can get into the use of English language from the point of view of certain words like consistent, right? So you have, like the majority of scientists, say this is the case. There's a consensus in this sort of argument, right? Where others, may have an alternative point of view, and if the results are such that we may not know exactly what is the correct answer in that case. So we always are on the lookout for something that goes against the grain, if you like.
Right. We want to see the black swan.
So when we talk about the dark energy, that makes up 70% then of this cosmic pie. The second major slice that we see there, which is kind of what we're going to focus on probably for the rest of this podcast, is something that we call dark matter. So that makes up roughly 25% of the universe itself. Now, dark matter, and I'll say more about this when we get into alternative slides here. So just to finish up the cosmic pie. So the dark matter is something we'll say about in the next slide, but notice that the third piece, which represents about 5% of the rest of the universe, and it's labeled here as ordinary matter. So that's the matter that we're made up of, Robert, you and I.
Yep.
I mean, that's the baryonic matter, as we say. We're talking about protons and neutrons, and then you could add other things in there, electrons and so on. So it's just the things that you and I are made up, the things that our Earth is made up of, our sun, other stars, so on and so forth, is made up of this ordinary matter. But that's a minority. That's only 5% of the total universe. So in that sense, the rest of the universe, 95%, is in this form of dark energy and dark matter.
Which we just don't know.
Now, dark matter itself has a very interesting history. In some sense, you can go back nearly 100 years to look at studies where there was the first hint of dark matter in our galaxy. Now, what is dark matter? Dark matter, you can think of it as matter that has gravity. Okay? We know that it influences its environment through the gravitational force. So, for example, if you sprinkle some matter throughout our Milky Way galaxy and you watch the orbital motion of things that you can see, like stars, for example, you will notice that their motion can be altered because of this gravitational influence of something new, this dark matter component. Now, when we look for the dark matter, we look to see what is causing this extra gravity, if you want to think of it that way, and we don't see anything. So as far as we know, this dark matter doesn't emit light. So it wouldn't reflect light, it doesn't emit light, and so it makes it extremely difficult to see directly in that sense.
Doesn't absorb light, so you can't even tell by the fact that it's blocking and there's nothing there.
So the major thing that we look for, and that's the reason how it was discovered in the first place, was through its gravitational influence on its environment. So anytime there's matter or energy around, it will have gravity associated with it. So this dark matter has gravity. It can affect things, but it's very difficult to detect directly, only through its gravitational influence. So back in the 1920s, there was a few studies that were done by Jan Oort and others who looked at the orbital motion of things that you can see, that give off light, in other words, stars. And what they described was that the stars were moving in such a way that it was not the way you'd expect them to move, given all of the matter you can actually see. That is, things that give off light. So that would include other stars, for example, even dust clouds and gas clouds. So the objects like stars orbiting the center of our Milky Way galaxy were not obeying the laws of orbital motion. Now, it was inferred at that time that there might be other stuff out there, other matter, that's affecting the orbital motion of things that we can see. And you wonder what this other stuff could be. Well, one way you could have matter out there that you can't see is just make it extremely faint, so faint that the telescopes that are available at that time in the 1920s weren't able to detect this material. So that's a form of dark matter in that sense, right? And so the ideal is there's something there. So people weren't quite sure about it. They're back in the 1920s. We didn't have a good measurement as we have nowadays, 100 years later, of the distribution of matter that's in our galaxy and so on. And so you can always hide faint things, in the disk of our galaxy. And if you don't consider those faint things, when you add up its contribution to the orbital motion of stars that we can see, then you're missing this material. You're missing this extra piece of gravity. So what we had to do is we waited until the 1930s where another form of evidence for dark matter was published. And this was done by Fred Zwicky. So this is the slide that you're seeing in front of you. And instead of looking at the Milky Way galaxy, this particular study looked at the motion of galaxies in a galaxy cluster called Coma. So the galaxies that are moving around in this cluster, you can tell how they're moving by look at how the light is shifted either to the long wavelength side or to the short wavelength side, something that we call the Doppler effect. So, Robert, do you want to explain a little bit about the Doppler effect?
I certainly can. The Doppler effect is simply if you've got a moving source of waves, okay, in the direction that it's moving, because the source has moved forward in the time that it takes to emit the next wave, the waves in the direction it's moving are shorter wavelength, okay? In the case of light, this will make them look bluer. Behind them, because it's moved further away before it emits the next wave, it stretches out the wavelength, makes it longer, and so that's what we call, in the case of light, a redshift. So if things are moving away, the light is stretched to longer wavelengths, and we call it a redshift. If it's coming towards us, it's a blue shift. That's all these terms mean, and it's pure Doppler effect and well understood.
In fact, everybody has experienced the Doppler effect when it comes to sound waves.
Yes.
And you can think of a motion of a car. Let's say at night you're stranded on the side of the road changing a car tire, and you hear a car approaching in the distance, and you hear the noise from the car itself. It's sort of a higher pitched sound than what it would otherwise be if it was standing, stationary relative to you. And you hear the car approaching, and of course, let's say it's 3 o'clock in the morning. Who's going to stop on side the road, right? You have to be very careful, right? And you don't know the person. It's a complete stranger that you see on side the road. So chances are any car that goes by at 3 a.m. is going to pass you.
Right.
Okay. So what is the sound that car makes then when it passes you? Yeah, you get that characteristic type of. Now, what is that, right? Well, when it's approaching you, the sound waves in this case are bunched up. They have a much shorter wavelength than they would be if the source of sound was stationary relative to you. And because it's been bunched together at shorter wavelength, a blue shift in that case, our ears detect that as a higher pitch. So that's that. And then when the car, in this case, passes by us and is heading away from us, all of a sudden, of course, the waves are stretched out longer than what they would be if the car was stationary relative to us. And we hear that as a lower pitch. So when the car passes, then it goes from high pitch to low pitch, and you get that characteristic type of effect. So we've all heard that, even if you don't know the physics behind it or why it happens. It's a common day, everyday type of experience. But the same thing applies to light, as Robert mentioned. We could measure the blue shift or the red shift and be able to calculate what is the relative motion of the objects relative to us. And so when Fred Zwicky looked at the motion of galaxies in the Coma cluster, what he discovered was something extremely interesting. That these galaxies were moving within the Coma cluster too fast, if you like, than the local speed limit. And otherwise, given the amount of material that you can estimate that the Coma cluster has, and how do you do that? Well, you can count up the individual galaxies.
Right.
we know how far away the coma cluster is, so you can estimate what is the total mass that you can see through a telescope in the form of the galaxies in this cluster. And what Zwicky discovered was that these galaxies are moving too fast given the amount of gravity that they're experiencing from the cluster itself. They're moving so fast, in fact, that they should be flying away from the cluster. That cluster doesn't have enough mass to keep them bound. So these galaxies have reached escape velocity. They would continue to move away from the cluster for all of time. But if that's the case for other clusters, why do we even see clusters? We literally see, hundreds of thousands of galaxy clusters spread throughout our universe. So the chance of every one of them being in this very special state where the galaxies are just moving away from the cluster itself would be extremely, extremely small in terms of that probability. So Zwicky then attacked us from a different way. He said it's probably more likely that the galaxies are indeed part of the coma cluster, and they are moving fast, way faster than what they should be, given the amount of mass I can see in the form of light coming from these galaxies, that is starlight, that there must be a lot more mass in the cluster that I am unaware of. And it's the combined gravitational attraction of all of this mass that you can't see, as well as, of course, of the mass that you can see, that when you add it all up together, there is enough mass that the galaxies are bound to the cluster itself, right, that they are not violating the local speed limit. And the question is, at this point, then, how much more additional mass do you need, then, to make sure that these galaxies are bound to the system? And he came up with a very large number. He came up with a factor of about 160 times more dark matter in this cluster than what is made up in the form of ordinary matter. Now, in the 1930s, when this was published, nobody really paid a lot of attention to it. I don't know if people read the papers back then and kind of said, this result is so weird, so off the normal trend, so unexpected.
He must be wrong.
That he must be wrong. That's right. So nobody believed him that there was this dark matter. In fact, nobody made the connection with the 1920s and the studies that were done with the orbital motion of stars in our own Milky Way galaxy and say, hey, maybe we're talking about the same sort of thing. That connection wasn't made at the time. Of course, as we say, hindsight is always 20/20, right?
It's 20/20, right.
Okay.
Or 2023 now.
There you go. Now, to kind of take the story along up to more modern times, and we really had to wait until the 1960s, into the 1970s, before we see some, really robust observations that started to be made about this dark matter problem. In the 1960s, several astronomers, including radio astronomers, were keeping track of the motion of gas clouds in the outskirts of our own galaxy and in other galaxies like the Andromeda Galaxy, other nearby galaxy that's similar to our own. That galaxy, the Andromeda, is about 2.5 million light years away. Mm-hmm. Now, what was discovered was that through radio observations initially, that these gas clouds are made up of hydrogen. So hydrogen is easy to observe at radio wavelengths. It naturally emits photons, radio photons, of a wavelength of about 21.1 centimeters. So with a radio telescope, you can detect this material. So what was discovered was that these gas clouds in the outskirts of the Milky Way and in the outskirts of Andromeda seem to be traveling a little bit too fast, faster than what you would expect them to be moving based on the amount of ordinary matter that you see in our galaxy and also infer that's in Andromeda. Now, this work really went forward in the early 1970s by Vera Rubin and Kent Ford. So they did some really classic observations of what we call the rotation curves of galaxy. And what they discovered was the robust detection of dark matter, not only in the Andromeda Galaxy, but evidence for that in our galaxy as well. So on this slide then, what we're illustrating here is what we call a rotation curve, in this case for the Milky Way itself. Now what's plotted on the vertical axis is how fast something is moving, the rotation speed, and the units here are in kilometers per second. On the x-axis, the horizontal axis, we have distance from the center of our Milky Way galaxy. Now, the units of distance here, they're not in miles, they're not in inches or kilometers, they're in kiloparsecs.
Kiloparsecs.
Okay, so that's sort of a standard measurement that we use a lot when we talk about distances within our galaxy, for example. Now, we had alluded to this a while back in a past podcast, but a parsec is defined as the distance that a star would be from the Earth, from the sun technically, if it would display a parallax angle of 1 arcsecond. So the idea is, you know, if you put your finger in front of your nose at a certain distance away and you look at your finger relative to the background with one eye, then you close that eye and open up the other one and go back and forth, you see your finger shifting back and forth. That's a parallax. And the further away your finger is from your nose, and when you repeat that sort of experiment, you'll notice your finger shifts back and forth at a smaller angle relative to the background. Well, that shifting back and forth then is directly related to a couple of things. Number one is the distance between your eyes, that we call the baseline. The other thing is the distance to your finger itself. The further away your finger is, the smaller is that parallax angle, and the closer it is, the larger. Well, if we observe nearby stars, let's say on one side of the Earth's orbit, and then wait 6 months later till we're on the other side of the Earth's orbit and observe that same star relative to the background, we know then we will see this parallax shift in angle if the star is close enough. And so one parsec is defined as if that shift, it's half of the total shift to be technical, if that shift equals exactly 1 arcsecond, then that star would be 1 parsec away. To convert it into other units that we know more about, if you convert it into light years, that works out to be approximately 3.26 light years. That would be the distance to a star if it was exactly 1 parsec away. And the distance that's labeled here on the x-axis is in thousands of parsecs, kiloparsecs. Okay. What we see here then is a measurement of how fast things are moving in the disk of our galaxy. So the sort of pinkish red color, which is labeled, you notice the sun is along that curve. That's actual observations. And the interesting thing is when you get to the outskirts of our galaxy, so you get to distances, let's say, of 30 kiloparsecs, 35 kiloparsecs on the far right, you'll notice that that curve is relatively flat for most of the distance from the center of our galaxy. Now, if you look at the distribution of light in galaxies like the Andromeda Galaxy and so on, and use that as saying, okay, our galaxy seems to be about the same kind of thing, right? Most of the light is near the central region of our galaxy, and where most of the light is located, chances are that's where most of the mass is located. Once you get outside most of the mass of the galaxy, we expect that these orbital motions should actually decrease. Now, the good analogy, of course, of that would be our solar system, right? And that's what we see here labeled in this dashed line as Keplerian motion, the orbits of Kepler.
From Kepler's laws of planetary motion that were later demonstrated why they worked out by Newton and his now law of universal gravitation.
Right. So if you look at how fast Mercury is moving in its orbit, Robert, and compare it to, let's say, the Earth moving in its orbit, which planet moves the fastest in its orbit?
Well, that'd be Mercury.
Be Mercury, that's right. In fact, we know how much it's moving in its orbit. That is how long it takes to go around once in its orbit relative to how far away it is from the sun on average, right?
Right.
That's Kepler's third law.
Kepler's third law. Yep.
So do you remember Kepler's third law?
Basically, the period squared is proportional to the semi-major axis squared. Cubed, sorry.
Right. And so in other words, if stars in the outskirts of the Milky Way obeyed Kepler's laws, in particular we're talking about the third law, then their rotational speed, their speed going around the center of our galaxy should fall along that dashed line. Now, do they fall along the dashed line, the observations, Robert?
Negative. They do not.
Yes. So they do not fall on the dashed line. They're relatively constant for a huge range in distance from the center of the galaxy. So, of course, you're left with trying to explain this. Why are things, gas clouds or stars, let's say, in the very outskirts of the Milky Way, why are they traveling so fast? Way faster than what we would expect.
If they're traveling that fast, then why aren't they flying away? It becomes the question.
That's right. So why is our galaxy stable?
Right. Why isn't everything just flying apart?
There we go. And so there must be, at least there's a way of explaining it, if we hypothesize that there is a huge amount of dark matter that populates our galaxy, then it's the combined gravitational influence of that dark matter plus the ordinary matter that allows the stars, especially in the out parts of our galaxy, the outskirts, to have the motion that they have.
Can I point something else out? The fact that it is flat out there at the outskirts also says that it's not matter that's concentrated into the center. It has to be spread out in the outskirts.
That's right. In fact, we can make the suggestion, and it seems to be valid as far as we can tell today, that there's this dark matter halo that our galaxy is embedded within. Now, you might think that this is something weird about our galaxy, but we see that in other galaxies as well. We look at the Andromeda galaxy, it has a flat rotation curve. We looked at other galaxies, they have flat rotation curves. We can look at elliptical galaxies, they have evidence for dark matter. In fact, every galaxy that we have observed, except for, which is actually interesting and a whole podcast on itself, a couple of dwarf galaxies that are in the Virgo cluster. Oh. Every other galaxy has evidence for dark matter. So it's clearly, one of these major things that spread throughout the whole universe. In fact, without dark matter, you can't explain the distribution of galaxies in our universe.
Oh, wow, that'd be right, yeah.
Now, galaxies are not randomly distributed everywhere. Mm-hmm. They're a structure to the distribution of these galaxies, what astronomers call large-scale structure. In fact, a way of thinking about it is like a giant three-dimensional spider web. We call it the cosmic web. So they're a filamentary-like structure. There are sheets and voids and these kind of things that exist in the distribution of galaxies spread throughout the universe. In fact, that structure would not exist the way we observe it today if it wasn't for the presence of dark matter. So the evidence for dark matter is everywhere. In fact, we can see evidence for dark matter in something that we call gravitational lensing. So Robert, do you want to say a little bit about this?
Basically, this was hypothesized by Albert Einstein when after he'd proposed his general theory of relativity that said that space and time are curved around a bunch of mass. And so what we finally we're able to observe is first off, what we would expect from that is that light coming from a more distant galaxy or galaxy cluster should be bent and hence focused in towards Earth, but in a three-dimensional matter if there's a large amount of mass in between us. And what we found with Hubble and a few other instruments, including James Webb now, is we see these nice little foreground galaxy clusters and smeared out in rings around them. And here I am gesturing with my hands like you can see me. Smeared out in rings around these massive clusters of galaxies are exactly what we thought. Focus light from background galaxies where it's warped through that space-time curvature. Now the problem is there's more warpage than the visible amount of matter that we can see in those clusters should cause. So, and I'll throw it back into your court.
Right, so we can use these gravitational arcs. For example, on the image of the cluster on the left side of the slide, you can see those beautiful arc-like features. There's, partial circle-like features that you see there. In fact, given the shape of those arcs, now those arcs, the light that you're seeing there, the bluish light, is actually coming from galaxies that lie far in the background of this foreground galaxy cluster. So as that light passes through the vicinity of that galaxy cluster in the foreground relative to these background galaxies, then it gets distorted. It gets disturbed, it gets sheared, it gets stretched out, and you have these arc-like features. It's the same kind of thing as, for example, let's say you had a champagne glass. So you take your champagne glass and then tilt it up towards the light. Make sure you empty it before you do the tilting, and you don't want to waste your champagne, so drink it. Right? You point it towards some light source, right? And you'll notice that if you point it off away a little bit from the light source, as you look through the bottom of the champagne glass and then pass it in front of the light source, there'll be a certain alignment where you see this nice ring around the light around the bottom of the champagne glass itself. So that's sort of what space is doing here. Space is acting like a lens in that case. Now, what's happening here, of course, that the space in the vicinity of this galaxy cluster is being warped by the presence of all the matter and all the energy that's there. We have the warpage of space and time, space-time. And the light that wants to travel in a straight line, coming from a background galaxy, when it passes through this cluster, because space itself is not flat, it's warped because of the mass of that cluster, then light takes the shortest path in warped space.
I was about to say, from its perspective, it is traveling a straight line.
That's right. So it gets deflected from a straight line path, as we would notice if it was flat space. So the amount of curvature that you see here, in other words, the shape of these gravitational lenses, they actually allow us to estimate what is the total mass and energy that's causing this warpage in this galaxy cluster environment or vicinity. And when you look at this, what you can estimate then, based on these gravitational lens features, is there is a lot more matter, usually a factor of 5 to 6 times more matter that's in this galaxy cluster than what you can actually notice by looking at individual galaxies using a telescope and estimating their mass, and looking at any other forms of matter that may be in the cluster. Those other forms of matter would include things like X-rays. Mm-hmm. Now, Robert, one of the things we discovered when we had X-rays telescopes put in space, by the way, why do you need to put an X-ray telescope in space? Why can't I just put it in my backyard?
Because 90 kilometers of atmosphere is a pretty good absorber of X-rays.
Right, so the X-rays get totally blocked by the Earth's atmosphere. So if you had an X-ray telescope and put it in your backyard, it would be useless for observing astronomical objects. So it's got to be put in space. So we had to wait for rockets to develop to the point that allow us to put X-ray telescopes above the Earth's atmosphere. And when we started observing the universe at X-ray wavelengths, one of the things we discovered was that a lot of these galaxy clusters, almost all of them, have this hot gas because we see extended X-ray emission coming from these objects. And this hot gas is tens of millions of degrees in temperature.
Now remember, folks, for astronomers, temperature is just a proxy for how fast the particles are moving. So this is still rarefied stuff on the order of 1 or 2 protons per cubic meter, but they're moving really, 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 really fast.
Now, Robert, if I had a container and it had gas in it at about 20 million degrees, and if I passed that to you, would you take it and hold it?
I wouldn't want to be anywhere near that.
I mean, that's because it releases a tremendous amount of X-rays. But those are the X-rays we can detect here near the Earth with our X-ray telescope.
Wondergoon has asked a question, so does that mean Superman shouldn't be able to see anything with his X-ray vision in the atmosphere? No. It takes 90 kilometers of atmosphere to block X-rays. So unless he's looking from space down to Earth, he will see just fine with X-rays.
I mean, the major contribution to the blockage of X-rays is the ozone layer. But the other thing is there are terrestrial sources that emit X-rays.
Right.
And those he could see.
Right.
Right? So if you had X-ray eyes and we're looking around standing on the surface of the Earth, you wouldn't be able to see the sun, you wouldn't be able to see any other objects out in space. But if there are any X-ray sources on the surface of the Earth, you can potentially see them, of course.
And so you'd see your doctor's office because it'd light up occasionally with a pop of X-rays when they were taking one of somebody.
Yeah, you go and get a dentist X-ray, right? You'd be able to see the emission coming from that machine, those kind of things.
Yeah. So I was going to say it's a good thing our atmosphere does block it because the sun does produce a certain amount of X-rays. So we would be constantly bombarding, our cells and DNA would be destroyed by the X-ray emission of the sun alone if it weren't for the fact that the atmosphere acts as a pretty good block. The atmosphere in total acts as a pretty good block.
Or you can go down the route of thinking about evolution.
Oh.
And what I mean from that point of view is if we did live on a planet whose atmosphere is such it didn't block the X-rays, maybe life would arise on this planet with this hardened shell-like structure.
Right. Or just with a system of chemical reactions that counter the damage done. But we don't have to worry about that unless we go outside the atmosphere, and then we better worry about it.
Or destroy it somehow.
Or destroy the atmosphere somehow, yeah.
You're going to worry about that. So with these X-ray emissions of galaxy clusters, then, we include that in the mass budget. And we still find that it's not enough mass, whether it's all the hot gas you add up, but all the ordinary matter in the terms of stars and galaxies and so on. It's not enough. We need 5 to 6 times more matter in these galaxy clusters to explain the curvature that we see in these gravitational lenses. So that is, once again, evidence for dark matter.
Yep.
Now, at this point, we're left with a conundrum. What is dark matter? As far as we can tell, dark matter does not give off light. Now, it may give off very little light, and what makes up the dark matter, whether it's in our galaxy or other galaxies, are things that are intrinsically very faint. So we have certain things that would give off a little bit of light. For example, a neutron star, right?
Okay.
It has a very low luminosity, as we say. Intrinsically, it's fairly faint. There are other stars, for example, like white dwarfs that are very faint. There are objects that quite didn't make it to the star stage. We call them brown dwarfs. They are failed stars. Objects that have a mass less than about 8% of the sun's mass. They would be intrinsically very faint. Well, in astronomy, we would say they have a very low luminosity. So
Right.
unless they happen to be very nearby, it would be very difficult to see these objects.
Mm-hmm.
The other thing is when we look very carefully for these type of objects, and there are ways of doing it, not just direct observation with a telescope. We've also had projects that run in the past where we looked for the gravitational lensing feature of these low mass objects that would be intrinsically faint.
Or occultation, where they pass in front of something and they would dim it or block it out completely for a time.
Right, and what we discovered was there's not enough, as far as we can tell, of these objects in the form of, it could be other planets, rogue planets or whatever, or it could be these white dwarfs or these neutron stars or these brown dwarfs. There doesn't seem to be enough of them. The density is not great enough to explain the flat rotation curve, let's say in our galaxy. So if we don't have enough of them, then we know that dark matter has to be made of something else. So one of the things that people are looking at today is black holes. Maybe that if you have enough of these black holes around, and they are the perfect candidate. Why? Number one, they don't emit light.
Right.
So black holes are not going to emit light. The other thing is they have a certain amount of mass. So if there's enough of black holes, if the density is high enough in our galaxy and in other galaxies, maybe that makes up the dark matter. Maybe that would be responsible for the flat rotation curve. Now, there is some subtle sort of arguments that people make based on actually what's called Big Bang nucleosynthesis. The fact that depending on the amount of hydrogen and helium that you form after the Big Bang, after the hot early phase to our universe, that actually puts some tight constraints on the mass density of the universe itself, things in terms of ordinary matter like baryons. And so this puts a constraint on how many of these black holes should be around. So initially, people dismissed the idea of black holes. Doesn't seem to be enough. And if you have too many, it would start messing up with the Big Bang nucleosynthesis. So it would start giving you numbers that were not consistent with observations.
Right.
So the big push nowadays is to try to make what we call these primordial black holes that were formed in the very early universe. And you can do tricks, if you like, quote unquote tricks, that if you make them early enough, they don't have as dramatic impact on the formation of these light elements, the hydrogen and the helium and so on in the early universe. But there's no evidence right now for these primordial black holes. I mean, that's one of the things, of course, that we look for is trying to figure out how would we see these things around us today if they existed. So in some sense, the majority of physicists now are relying on the fact that dark matter might be in the form of a subatomic particle. Now, it could be more than one. Nobody said there had to be one candidate for dark matter. Maybe it's made up of 3 different types of subatomic particles. Nobody knows. Now, what is the beauty of a subatomic particle, Robert? Why would that be a good candidate then for dark matter? Can you think of some things?
I can think of a few reasons why it might be a favorable candidate. You could have a whole lot of them scattered throughout in a nice cloud, and you wouldn't be able to see it. You wouldn't be able to detect it. You'd just, it'd be a soup that essentially you were swimming, a soup of water, clear liquid, I guess. So that would be a nice factor. You wouldn't have to worry about it slurping up the earth because it comes racing through like a black hole would or anything else. Other things I can think of, it would make it difficult to detect, especially if it's only interacting gravitationally, which it's proving difficult to detect. So it would fit that category. But it would also make it where it's not undetectable. You just got to contrive the right scenario, the right situation for it.
Now, can you think of a subatomic particle that would be a perfect dark matter candidate at first glance?
At first glance, I would think neutrons. I would. But then again, neutrons are unstable and decay into protons and electrons.
Right. What about a neutrino?
Oh, neutrinos. I don't think about them, to be honest.
Now, neutrinos have the benefit that they don't have an electric charge.
Right.
I mean, you can get that from the name little neutral one, neutrino. And the neutrino, because it doesn't have an electric charge, then it's not going to emit light, and it's not going to interact with light. But what we discovered was relatively recently, it wasn't that long ago, and then really in the 1990s, the evidence came forward that showed that neutrinos have a little bit of mass. So because they have mass, then they would have gravity. And neutrinos, they interact very weakly with ordinary matter, and so they're very elusive from that point of view.
Don't they have to be aren't they going to be traveling at near the speed of light, though?
Because they have a little bit of mass, right? That clearly would be they would travel less than the speed of light.
But still very fast.
Right, and so the argument that was made at the time was we don't know exactly what the neutrino mass is. There are several different flavors of neutrino. There's the electron neutrino, the muon neutrino, and the tau neutrino. In fact, experiments that were done not too far from here in South Dakota by Raymond Davis was looking for electron neutrinos coming from the nuclear reactions that's occurring inside the very center of our sun. And what he was discovering was that he was only detecting about 1/3 the number of electron neutrinos that he thought he should detect.
But he found their antiparticle.
Well, no, what was discovered was evidence using other particle detector like the Sudbury Neutrino Observatory and the Kamakade experiment in Japan, was neutrinos actually can change types. So as the electron neutrino is emitted from the sun on its way to the Earth, it actually can change flavor or type. So by the time it arrived on the Earth, it was no longer an electron neutrino, it was a muon neutrino or a tau neutrino. And the experiment by Davis in South Dakota was not sensitive to those other 2 types of neutrinos. They were only sensitive to the electron neutrino. Okay. And so that's how that was quite a problem for many years. It's called the solar neutrino problem.
So I remember that.
Yeah, so scientists, what they did was they say, oh, let's just reduce the number of neutrinos that get output by our sun to make it consistent with the observation. So then if you start changing the solar model, you start changing the temperature, the rate of production of energy in the core of the sun, then that will affect other things that you actually measure directly, like the energy output of the sun, its luminosity. And if you lower the temperature of the core of the sun and reduce the reaction rate so you produce less neutrinos, you also decrease the luminosity of the sun, and that is against or not consistent with observations that we make in space of the sun itself.
And so you wad up that paper and you toss it over your shoulder and file it in 13.
Right, and so there were ideas that were put forward about this flavor mixing of neutrinos, and ultimately that was shown to be the case. So we figured that out, but we just don't know the exact mass of a neutrino. People are doing experiments to try to determine that more precisely today. But we do know they have a little bit of mass. So right away, because they don't have an electric charge and they have a little bit of mass, you would think it was the perfect candidate for dark matter. The problem is there's not enough neutrinos. In that sense, they're not massive enough.
Okay.
And so neutrinos would be a small fraction of the dark matter, but it's not the huge majority that we're still looking for. So we're still on this trail of trying to uncover, if it is subatomic particles, what is the dark matter particle? And if there's, of course, it could be more than one type. The slide that you see here is kind of an illustration of some of the experiments that are running today. The idea is that if you have an incoming particle, and once in a while it will make, if you like, a head-on collision with the atoms that are in a fluid. Let's say it could be water. In this case, you usually use heavy water.
Usually use heavy water, right?
And when an incoming dark matter particle makes a direct collision, then that energy of that motion will go into the particle and it cause it then to decay into other parts. It may release electrons, for example, or it may cause it to break apart. And these electrons then would be traveling, if they have enough energy, traveling faster than the speed of light in that fluid. Now that doesn't violate the special theory of relativity. The special relativity states that nothing travels faster than the speed of light in the vacuum of space. That's the important thing, the vacuum of space. In fact, physicists can do experiments where light travels through a substance and it travels at such a slow rate of speed that you can actually walk faster than the speed of light in that substance.
Yep.
Right.
And Wondergoon is asking another question: is there a mathematical value that is used in equations for dark matter? And my guess would be that there are several, because it appears in general relativity and its metrics.
The metric, yeah. So the thing what you look for is, for example, what is the contribution of dark matter?
Right.
And so you can use, for example, the rotation curves of galaxies. You can use the distribution of the gravitational lenses we see in galaxy clusters. You can even apply it to other things we haven't talked about, baryonic acoustic oscillations, the cosmic microwave background, and that's why we come up with the cosmic pi at the very beginning.
And getting back to your question, Wondergoon, each one of those things he's mentioning have their own set of equations that are working for it. So all of these equations are basically pointing in the same direction, is kind of why we're saying, there's got to be something there, because they're pointing the same way from various directions. They're all pointing to the same place. So, when it starts getting into the point of, if it walks like a duck, quacks like a duck, and flies like a duck, it probably is a duck.
Right, and the thing to note here is that on average then we can say that the dark matter then is about 5 times the amount of ordinary matter. That seems to be a consensus on the value that we get with all these different techniques that we use to measure it.
Right.
Now, these subatomic particles, as you see here in this slide, as they collide with ordinary atoms that's in the fluid and the heavy water that's in a lot of these detectors, then they release these electrons that travel faster than the speed of light in that fluid. And they release what's called Cherenkov radiation. And this light that's emitted, it's blue light.
Very blue.
It can be detected by photocells. So the things you see on the top, circular in pattern, those are photomultiplier tubes. So we can use those to detect this light. And then from that information, you can backtrack then where did this occur and get some information about the incoming particle in terms of its properties.
This is, in fact, one of the reasons why most of these neutrino and other exotic particle detectors are in the bottom of old mines, is how, one, contamination from things like cosmic rays, but number two is, where do you go to get it dark enough that you don't overload the photomultiplier tubes with background light?
Yeah, so it's mostly cosmic rays.
It's
right?
mostly cosmic rays.
Yeah, because we're in a bath of these particles that you can't see, and they're everywhere, bombarding our bodies continuously. But we know what those objects are, right? They're the ordinary matter. But we want to get to a place where all that gets shielded out. So then hopefully the only thing that we detect is the dark matter candidate.
Right.
Now, it's interesting to know that these detectors have been running literally for decades now. And there's never been a confirmed detection of dark matter.
Right.
But we're still looking. But it's actually getting interesting because a lot of the properties that we assumed dark matter would have, and you always have, some general ideas of the range of the masses and the energies that we expect these particles to have and so on, we've already covered almost all of that area. It's like assuming that you're looking for a watch, and the watch is somewhere in a baseball field somewhere. Well, how do you find that watch? Well, you can scan in a nice regular pattern, grid pattern, back and forth across that field, and then finally stumbling across your watch, hopefully. But now we're getting to the point where we've almost covered all of the baseball field, and yet we don't see the watch.
Right.
So things, I think, are going to get really interesting from the dark matter point of view going forward here in the next decade or so.
Right.
We're getting to the point where we start having to look at some really sort of bizarre properties of dark matter.
That, or we have to re-examine some of our old candidates and start going, well, what are we not seeing here maybe?
Exactly. So this is a very interesting sort of thing, and the story is yet to be concluded on dark matter.
Yep.
But anyways, thank you very much for watching today. I just wanted to finish with a quote that we usually finish with. And Robert, when we do quotes, and we try to do a new quote at the end of every podcast, eventually we're going to run into Yogi Berra.
Absolutely. I mean, one of the greatest quote meisters out there.
So the quote I have today is from Yogi Berra, and it is, "You can observe a lot just by watching." Now, my favorite Yogi Berra quote is, "When you come to a fork in the road, you take it," but we'll use that some other day.
Yep. I actually like when he used to appear on Aflac commercials, and he made the comment, "They pay you cash, which is just as good as money." And I guess we'll leave you on that one.
Now, right, I just want to say that the next podcast, don't forget, is coming up next Tuesday. That's on February the 28th, the end of the month at 3 p.m. Central Standard Time. And remember that if you're interested in science, and if you're a high school student, or if you're a student in general and want to get back into learning things about physics and STEM fields, don't forget to consider the University of North Dakota, the College of Arts and Science, and in particular, Department of Physics and Astrophysics.
Come have fun with us.
Thank you very much.
All right. See you next week.
Bye.